So welcome back to Chemical Engineering Thermodynamics. We're still in Unit 1 and we're going to be continuing today with calculations. Let's look at what we're going to be covering. So we'll go into the different calculations as it relates to kinetic energy, potential energy, as well as internal energy. We'll also review energy transfer and focus on energy balance. Now these are key areas and key fundamental calculations that would have you would have started while you did elementary principles of chemical engineering. So be sure to review those notes. They're also on the class website prior to moving on into these calculations. Okay, so let's look at kinetic energy. So now from lecture 1, we realize that kinetic energy is due to movement, motion of an object, or let's say a flowing stream, right? Now, in order to calculate the kinetic energy of a system or an object, we use EK, where EK represents the kinetic energy is equal to half mu squared. So m would represent the mass and u squared would represent the square of the velocity. Now if you notice in this example, we see EK with a dot over the E. So normally when we see a dot over, let's say, a variable, it represents rate, meaning you're dividing by a time unit. So in this case, half mu squared, m would have the dot, which suggests that m would be our mass flow rate. So let's take a look at this example. So we have a body of mass 3 kilograms and it's moving with a velocity u 5 meters per second. So our mass in this case is 3 kilograms. Our velocity is 5 meters per second. So if you notice, we set up our conversion table in order to do our calculation. So if we just calculate it directly, we'll find that our units are in Newton meter. However, we want to have our energy units, which is in joules, so we compensate for that by using the conversion factor, where 1 Newton is equal to 1 kilogram meter per second squared. Let's look at potential energy. So as previously discussed, potential energy is due to the position in a gravitational or electromagnetic potential field or due to the height of center of mass of an object above a reference point. So let's examine how to calculate this. So some books may refer to potential energy using the variable P subscript E, or you may find E subscript P, as in the case in this slide. So we have EP being equal to mgz. So let's define our variables. So m represents the mass of the object. It can also have the m dot, which would be the mass flow rate of the object. G is our acceleration due to gravity, which is 9.81 meters per second squared. And Z is our height relative to our reference point. So in this example, we have the object being 3 kilograms and the height above the reference point being 10 meters. So if we would like to calculate the potential energy, we simply multiply the given variables. Of course, you would need to know what G is, which is something you should know by heart, which is 9.81 meters per second squared. So we have 3 kilograms times 9.81 meters per second. Multiply that by 10 meters. Of course, you would need to do your conversion in order to get the units in joules or in joules per second as well. Now let's review internal energy. So as previously discussed, internal energy looks at all the sum of the rotational, vibrational, electromagnetic energies of individual molecules, atoms, subatom particles moving around a body of material or in a flowing stream. So it takes into consideration everything from a molecular or subatomic level. Now, the internal energy is not something that you can just get up and calculate. we have to look at it from different states. So in order to calculate it, we have to realize that there are two forms of energy transfer between a system and its surrounding. And the first one is heat. And heat, we use the variable Q, where the unit would be kilojoules, or we use Q dot, and of course the Q dot would suggest a rate, which is kilojoules per second. So of course heat is energy transferred as a result of a temperature difference between the system and the surroundings. Now work, our variable is defined as W, or we can also have W dot, where the unit is kilojoules per second. So work is the other way in which a system can have its energy, right? So the energy is transferred by mechanical motion or an electric current. So we define work as positive if work is done by the system on the surroundings. So therefore, our total energy of our system is the sum of our kinetic energy, our potential energy, as well as our internal energy. So remember, the energy can only be transferred as heat or work. We'll now examine the energy balance on closed systems. So I want you to envision this system where we have a piston with gas, and this gas would have, let's say, a number of moles. It would have a temperature T1, a pressure P1, a volume V1, internal energy U1, and kinetic energy K1, and potential energy P1. And this is at time equal 0. Now remember, we said that there's two ways that we can transfer energy in and out of a system, right? And that is through heat, which is Q. So you notice that arrow where the Q is entering our system, which is our piston. And because we've added Q to it, meaning we added some heat to it, we'll have the gas expanding, right? So the work will be done and the gas will push the piston up based on this expansion. So now this is now a state 2. So at state 2, we'll have the number of moles, we'll have temperature T2, we'll have a new pressure P2, a new volume V2, internal energy U2, kinetic energy EK2, EP2 for potential energy, and time T equal TF, right? This is our final time. Now the process may involve heating or cooling in terms of our temperature change. So if we have cooling, we'll have our compression or decompression when we have a change in pressure. And of course, a phase change, which can all lead to a change in our volume. So if we look at our change in temperature, it would be the difference between the two states, right? So it would be our T2 minus our T1. If we were looking at our change in kinetic energy, it would be EK2 minus EK1. So the difference would be, for all the variables, would be from state 2 to state 1. So you can now find out, okay, what would be the change in volume, right? So the change in volume would be our V2 minus V1. And you can do it for the different variables from our state 1 with our piston to our state 2 when we had the expansion of our gas. Now, if we're supposed to recall that previous equation where we had the total energy is equal to the kinetic energy plus the potential energy plus our internal energy. So remember that Q and W are the only ways in which heat can be transferred in and out of our system. So if we say that our input minus our output would give us the total accumulation in our system. So this is where we get the first law of thermodynamics for a closed system. So we have Q minus W is equal to delta EK plus delta EP plus delta U. So our net energy transferred into our system is equal to the final energy state minus our initial system state of the system. So we look at remember we had the two pistons, so we'd look at everything at the start where we had our piston with all our initial variables, and then in our state 2 we'd look at the system again with all our final variables. Okay, now if we simplify our first law for our system, we can eliminate certain variables, because that is the whole essence of doing an energy balance. We need to simplify our equation based on the variables that we have, or the things that are happening in our system. So if there is no acceleration, there's no movement, sorry, then we'll have our change in kinetic energy being equal to 0. If our system is not moving vertically, then our change in potential energy would also be equal to 0. And if there is no interactions or phase change or temperature, etc., then our delta U would be approximately equal to 0. So if we have no temperature difference between our boundary, or it's like a perfectly insulated system, there will be no Q, so no heat, right? And if we have no moving parts, no electrical currents, no radiation flow across the system boundary, then our work is 0. So what we have just done, we have just looked at all the different ways in which we can simplify our energy balance on a closed system. So it's basically, we have the overall energy balance where we have Q minus W is equal to EK plus EP plus U. And then we now need to simplify this equation by looking at the individual variables. So we assess our system. Is there any moving parts? Is there any work being done? Is there any temperature difference across the system boundary, etc.? And from doing that, we can further simplify our energy balance on our closed system. So far, we have examined heat and work calculations. Now, how can we look at the internal energy? How can we calculate the internal energy when we didn't really examine a formula? So let's go into that right now. So the true value of U, which is our internal energy, is never truly known for a given state. However, both heat and work can be measured with relation to the different states for a closed stationary system. And from that, we'll get that delta U is equal to Q minus W. So if we have both our heat and our work, we can calculate the change in our internal energy. But what happens if we only have our, let's say, work, and we want to calculate our heat? How do we now come up with our internal energy if that value is not given, let's say, in the problem or in our system? Now, what we have to look at is our specific internal energy. Now, by examining our steam tables at the different variables, whether it's temperature or pressure, etc., we can look up our internal energy, which would be our specific internal energy. So the change in specific internal energy is equal to our change in internal energy divided by our number of moles, or number of or mass, because some tables, they'll give you the specific internal energy in terms of mass, or you can get it in terms of the number of moles. So once we go into reading our steam tables, we can understand how to manipulate it, or how to use these relationships to calculate our specific change in internal energy or our change in internal energy. Now let's examine energy balance on an open system at steady state. So in this case, we have our system, we have different mass entering our system and leaving our system, right? So now for each of these variables that are entering, we have a corresponding one that's leaving our system. For example, if we were to look at M1, we have U1, Z1, T1, P1, V1, etc. And leaving our system, we also have M1 out, and or U1, Z1, T1, P1, V1, etc. Now, in our system a while ago, we also had heat being added to our system, and we also had WS. W subscript S is our shaft work. and it is work done by the system on the surroundings, which can be through moving parts. It can be pistons, propeller, turbines, or in an electric current, etc. And we also saw we had the mass as well, that's both entering and leaving our open system. Now, in order to look at the energy balance at a steady state, we go back to our first law of thermodynamics. Now we have an open system. Our first law goes back to delta H. Once we see this little bar, not a bar, it's more like a cap on top of a variable, it's looking at the specific, meaning you're dividing by mass or by mole. So in this case, we have delta H is equal to delta U plus P delta V. We also have, when we look at the different states, because remember we're looking at the initial state and our final state. So the U that you see in this equation, the delta U with our cap, remember it's specific, is looking at our U final minus our U initial plus our P final, V final minus P initial, V initial, where all these terms are specific. Specific meaning we're dividing by mass. So if you look in our steam tables, you'll see the specific enthalpy values. So enthalpy, just like internal energy, they're both state functions, meaning you can't just get up and calculate them exactly. You have to look at them from our initial state and a final state. And then because it's specific, you will now need to know the mass or the mass flow rate of the system in order to get the exact value. So it is a state property, it's immeasurable, and it's heavily dependent on phase. It's moderately dependent on temperature and slightly dependent on whether it is a real gas, liquid, or solid. And it's independent on the ideal gas or on pressure. So in the same way that the internal energy can be determined from one state to another, the change in enthalpy can be determined from one state to another as well. So when we're looking at our first law, delta H is equal to delta U plus P delta V, we are looking at it from a state perspective, meaning a final and an initial perspective, right? So we'll also look at how to read the steam tables. And if you still have your elementary principles of chemical engineering textbook, you can look at these tables in our B5 to B7. Also on our class site, you'll notice that I have placed the steam tables file. So we'll be looking at that file when we're going through learning to read steam tables and learning to do calculations for internal energy as well as for enthalpy. So when we're looking at the balance on the open system, it deals with our enthalpy as well as our internal energy and our change in pressure and volume. Now remember in that initial diagram that shows the work being done, right? We had WS. So WS is our shaft work. Now, the net work that's done on an open system will be due to the different types of work. Because remember, we can have flow work, which is the work done by a fluid at the system outlet, minus that from the inlet. And we can also have shaft work, which is the work done by the process fluid on a moving part. So now the net work would be the WS plus the WFL. So when we have a balance on an open system at steady state, we can have our flow work, because remember, we're not looking at flow work, we're looking at our volume change and our pressure, right? So WFL would take into consideration that P delta V term. So the first law of thermodynamics for an open system at steady state would be Q minus WS is equal to our delta U plus P delta V. So remember, our P delta V term would be like looking at our flow work, right? Plus EK plus EP. And of course, we can simplify that, and we end up with Q minus WS is equal to delta H plus EK plus EP. So in this bracket where we have delta U plus P delta V, if we recall from the first slide, delta U plus P delta V is actually our enthalpy. So that's why in the second line, we have delta H replacing that entire term right there. So now we've come to the end of Unit 1, Lecture 2. So the next steps is to attend our seminar session, which is a live session. We'll be looking at the tutorial review, and also I'll take any questions that you may have based on the current lecture as well. Now, you also have some individual work, and it's essential that you guys complete the individual work prior to attending the seminar. I needed to write down and familiarize yourself with equations associated with the key concepts and definitions, namely how to do the energy calculations for kinetic energy, potential energy, internal energy, as well as enthalpy. I needed to also work all the tutorial questions. In order to do that, you have to go through the STEAM tables. There's a video on our class website that looks at STEAM tables. Please review before attending the seminar session. I will also do a recap of reading STEAM tables as well. I needed to also practice two-point linear interpolation, as this will form the basis of looking at reading our STEAM tables. And of course, ensure that you read the chapters for the unit.